Okay, so our searching algorithm that we have to deal with is this one, first bad version. And in this question, we are a product manager, and currently we are leading a team to develop a new product, right? Unfortunately, the latest version of our product fails the quality check. And since each version is developed based on the previous version, all the versions after a single bad version are also bad, right? So suppose we have n versions, which range from version 1 all the way to version n. Suppose we want to find out the first bad one, which causes all the following ones to be bad, right? So we're given an API bool of isBadVersion, where we pass in a version, and it returns whether the version is bad or not. So we're supposed to implement a function to find the first bad version, and we should minimize the number of calls to the API. So for example, our n equals 5. So this tells us how many versions there are. So it ranges from 1 to 5 versions. And it tells us here that bad is equal to 4. We're not given this information. We're supposed to determine which version is the first one that is bad, right? So the explanation for this example would be like, we call the API on version 3, and we get that this is not a bad version. If it returns false, it's not a bad version, but if it returns true, it is a bad version, right? And we're supposed to find out what's the first version that returns true out of the 5. So here we call 3 and we get false, which means that it's a good version. Here we call 5 and it returns true, which means that it's a bad version. But now we have to see if this is the first one or not. So we check between 3 and 5, and then we check 4, right? And we see that this one also returns true. So that means that 4 is the first bad version out of the 5 that are in here, right? So that's kind of the explanation of the problem. Let's look at a few other examples. So for this example, we have false, 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 true, true, true. And this 1, 2, 3 corresponds to the versions from 1 to 8. So we could visually see that our function should return this, number 6. So version 6 is the first one that is true, where it's a bad version. And how would we be able to find out that 6 is the first one? So of course we could do a linear search, right? So we could iterate through the versions starting at 1 and ending at 8. And we just check, okay, is this version, like we have a little counter, right? Let's say I is equal to 1. We check, okay, is this one true? If it is, then I just return I, right? And if it's not, then I just increment I, right? So if this one's false, I just increment. Okay, so now I is 2. Check if this one is false as well. It is false, so we're just going to increment again. Check this one, right? Is it false? Yep. So just increment again. Now I is equal to 4. Check this one. This one's also false. Increment again. And then check this one. This is also false. Increment again. And we keep doing this until we find the first true one. So we check this one, right? And we find out that version 6 returns true. So then we would just return 6, right? So we could do that. But what's the problem with that? Is that we're making 6 calls to the API, right? We're supposed to try and minimize the number of calls to the API. So this algorithm that we just thought of, the linear search, as we like to call it, is O of n, right? That's O of n runtime. So we make 6 API calls, and that's how we get our final answer. But we can do better than that, right? We could do a binary search. And essentially what we do in a binary search is we have a start and a finishing range, right? We have 1 to 8. So what we can have is our starting index, which would be our 1 in the beginning, and then our finishing index, which would be this over here, number 8. Version 8 would be our finishing index. And what we're supposed to do is find the midpoint. So we look at the midpoint between S and E, so start and end, and we see, okay, it's going to be 1 plus 8 divided by 2. So 9 divided by 2 is 4 if we use integer division. So what we do is we check this one. We check version 4. And is version 4 true or false? So we find out that version 4 is actually false in this case, right? So if it's false, what we want to do is we know that our first true one is going to be to the right of this, right? It's going to always be to the right of all the false ones. We want to find out where the versions actually start to go bad, right? So we know this is good, up to here is good, so we want to be checking to the right of this. So what do we want to do if we find out that this is false? We want to adjust our start to be at this midpoint plus 1, right? So we're going to move our starting index right here, right here. And then we're going to start checking for the indexes between these two now, right? Because we know our first bad one is going to be between this range at this point, right? So that's what we're going to do. So now what we do is we check the midpoint again between our new start and our new end, and we look for a midpoint. 5 plus 8 divided by 2 is 13 divided by 2, which is 6. So we know that this is going to be our midpoint. And this one is true, right? And anytime we know that this one is true, um, basically we have to adjust the end, right? So we're going to have to move this end to our midpoint minus 1. Okay? Move this over here. And at this point, what we do is we continue our algorithm one more time, as our start and our end is the same. We're going to say, okay, what's the midpoint of this? It's going to be 5 plus 5 divided by 2, which is going to be 5. So we're going to check our fifth version, and it's false, right? So at this point, we're going to adjust our start to our midpoint, which is this one, plus 1. So we're going to move our start right here. And once our end becomes less than our start, we're going to break out of our function and then return our start version. Okay, we're going to return our starting version, and this is going to be the first bad version that we have in this example. So what do we notice about that? We notice that we made 3 API calls, like 3 calls to the API in order to get the first bad version. And that is why this binary search is so powerful. We are able to basically cut our subset in half every single time we do a search. So first our search was like this, right? And then we found out that this was false. So then we know that our answer is going to be to the right of this. So then we check all of these, which is the second half, right? And we found out that this one was our new midpoint, and it's true. So then we check all the elements to the left of it, and still in this range. So we just check between these two, right? So we continuously break our problem in half each time. Our searching, like our entire range was 1 to 8. We constantly are breaking our current search in half to find our answer, right? So let's look at it in this example as well. So once again, we'll have our start at number 1 and our end at number 8. And we'll just break through this problem again. So start and end, so 1 and 8. We want to find the midpoint, so 1 plus 8 divided by 2 is going to be 4 once again. So this is our midpoint. And we check if this one is true or false, right? And if it's true, we know that we're going to have to be checking to the left of this, right? Because we found this one to be true. And now we want to check if it's the first true, right? So we want to check if there's any more to the left that are true. So what we do is we break this into this little problem now. So we adjust our new end to our midpoint minus 1 to cover this range right here. Let me redraw it. This range right here. We want to cover these range and find if there's another true inside of here. That's basically what we do, right? So now we have this new range, and we want to find the midpoint again. So 1 plus 3, which is 4 divided by 2, is going to be this one. We check if this one is true or false, and it's false, right? So we're going to be checking to the right of this one now, because anytime it's false, we're going to be checking to the right. Anytime it's true, we check to the left, right? So we adjust our start to be to our midpoint, which is this one, plus 1. So we move our start right on our E. So now our start and end are going to be the same. And now we're going to check the midpoint between our start and end, so they're both 3. So we're going to be doing 3 plus 3, which is 6, divided by 2. And so we're going to be checking this one, right? And we find out that this one is true, right? And anytime that this one is true, we're going to be moving our end to the midpoint minus 1, right? So here we're going to move our end right here. And that's it. Once our end becomes less than our start, we're going to be returning our start variable, and that's going to be our first bad version. Right, so now that we actually understand our algorithm, we could begin to implement this. So once again, we're going to have our starting variable, and we're going to start it at 1. And we're also going to have our end variable, which is going to be at n, right? So given that, we also want to begin our while loop. And as I said, it's going to be while our start is greater than or equal to our end, and we're going to break at any time that our end actually becomes lower than our start, okay? And the first thing that we're going to do in this while loop is calculate our midpoint between our current start and our current end, right? And the way that we do that is we have our mid, and it's going to be equal to our start plus, we're not going to do start plus n divided by 2, as I may have done in the example as I was going through it, because that could cause a integer overflow, or we could exceed the limits of an integer, because like if we have 1.5 billion plus 1.5 billion, which would be both of our start and our end, we're going to get 3 billion, right? And that gets over the integer maximum. So what we actually do to prevent that is we do start plus end minus start divided by 2, okay? So n minus start, if they're both 1.5 billion, is going to give us 0, right? And we divide this by 2, which is going to be 0. 0 divided by 2 is 0. Plus our start, which is 1.5 billion, and that's going to be our midpoint, right? So that's actually how we calculate the average between two numbers with ensuring that it's not going to overflow, okay? So we do that, right? And then we want to start beginning with the checks, okay? So first we want to check if the midpoint is a bad version, right? So we could call on the API, as you said here, the isBadVersion API is called like this. So isBadVersion of midpoint, okay? So if this is a bad version, what did we want to do? So we check the midpoint, right? For example, if our, like remember when our start was like here and our end was here, so we found that this was the midpoint between it, right? We checked if this one was true or not, but this one is false. So when it's false, we want to be decreasing the size so that we want to be setting the start to the midpoint plus 1. So we want to be moving our start here. But if it's true, as I said, we're going to be moving our end to our midpoint minus 1. So our end would be here in this case, okay? So if our thing is true, we're going to be moving our ending variable to our midpoint minus 1. So that's what we're going to do. So if it's a bad version, our end is going to be equal to midpoint minus 1. Otherwise, so if it is false in this case, if we find a false, we're going to be moving our start to the midpoint plus 1, okay? So else start is equal to mid plus 1. And that's our entire algorithm for our binary search. And at the very end of this entire while loop, we're just going to return the start as I mentioned. And yeah, so we can run this and check if this works. Oh, it turns out it doesn't work. So if it's a bad version on the midpoint, what do we do wrong here? We can break this up. So our start is equal to 1. Our end is equal to n. Oh, sorry. I put our start is greater than or equal to. It's supposed to be less than or equal to, right? We're supposed to be checking that our end is constantly greater than or equal to our start. And once it becomes lower than it, then we know to break out of the loop, okay? So that was just a little mistake on my end. But that should work now. And yeah, so that's accepted. So remember when we were doing the linear search? The time complexity of that one would have been O of n, right? Because if the first true one was like the last one, version 8 would be the last true one, we'd have to go through all of these and check all of them, and then we'd check the last one, and we'd have to make 8 API calls before we find out that this is the first version. That is bad, right? So that's a linear search, so that would be O of n. But this algorithm basically cuts our searching size in half each and every time, and the time complexity of that is simply O of log n, okay? O of log base 2n, but time complexity is O of log n. And our space complexity, as we only have our start and ending variables, our space complexity is just going to be simply O of 1.
If you like this video, make sure to check out my course on Udemy where I go over how to approach and solve LeetCode's top interview questions in Java. This will help you get more comfortable applying concepts like arrays, strings, linked lists, binary trees, dynamic programming, object design, and many other concepts in order to solve problems effectively and ace your interviews. So if you're interested in it, feel free to check it out through the link in the description. And with that being said, I hope you guys have a good rest of your day, and I'll see you in the next video.